All right, we got a frog jumping towards a wall. Every time it jumps half the distance to the wall. So in its first jump, it's going to jump half a meter, say, and then on the second jump, it'll jump half of a half, which is a quarter, and then half of a quarter, which is an eighth, etc., etc. So this is a geometric series, but it's infinite because he keeps on jumping that half distance. He's never going to get to the wall. So A is a half, R is also a half, and n is infinity. So if we plug this all into the formula for a geometric series where we know the number of terms, we get Sn equals a half times 1 minus a half to the power of infinity all over 1 minus a half. So the problem here is we got to figure out what is a half to the power of infinity. So we're just going to play with it. I'm going to put a half to a bunch of different powers onto the calculator and write them out and see what we get. So a half to the power of 10, it's going to be basically 0 point and then 3 zeros and then a 976. Half to the power of 20, 0 point, 1, 2, 3, 4, 5, 6 zeros and then a 9. Half to the power of 30, now it's 9 zeros and then a 9. Half to the power of 40, it's a whole whack of zeros and then a 9. Half to the power of 50, well, it's even more zeros. Here we go, writing them all out, and then 888. Okay, here's a half to the power of 60. It's even smaller number. Half to the power of 100 keeps on getting smaller and smaller. As we go to a higher power, this keeps getting smaller, but people say, well, it's not 0 because that's 788 at the end. Half to the power of 150. Holy moly, lots of zeros and then 700. It's getting really, really tiny, but still there's something there. If we go to a half to the power of 300, it's 4.9 times 10 to the negative 91. I'm not going to write that out, but basically that's 90 zeros and then 490. If we go a half to the power of 350, the calculator says it's 0, so I don't want that. So let's try a half to the power of 328. It is 1.83 times 10 to the negative 99. So that's like 0.000098 zeros and then the 183. That's actually the smallest number the calculator can handle. A half to the power of 329, the next one, is 0. The calculator can't handle it anymore. So basically there's something there, but the calculator just can't handle it. And it's only at a power of 329. Consider a half to the power of 1,000, or a half to the power of 1,000,000, or a half to the power of 1,000,000,000. Like, we're not even, 329 doesn't even compare to 1,000, let alone 1,000,000, 1,000,000,000, a trillion, a Google. All these, there's so many massive numbers out there that what we do in math is we can never even get to infinity, but that's where we say it finally equals 0. All of these, there's something there, but then finally, if you could actually get to the infinity, it would equal 0. In fact, we say any value that is basically less than 1 but greater than 0, but then also negatives as well, so it could be between negative 1 and 0. If you go to the power of infinity, they will equal 0. So what we typically say is that if the absolute value of r is less than 1 but greater than 0, then r to the power of infinity equals 0. What this does for a froggy, if we go back to the froggy jumping towards the wall, is now we go, okay, that half to the power of infinity is 0. So that means s infinity equals a half times 1 minus 0 over 1 minus a half. 1 minus 0 is 1 times a half is a half. 1 minus a half in the denominator is just a half. Half divided by half is 1. And the froggy got to the wall. Yay, good for the froggy, he did it in infinite jumps. So then our formula, though, is that we always say Rn equals 0 when n is infinity, but r has to be between 0 and 1. Well, the absolute value of r is between 0 and 1. So again, it's anything between negative 1 and 1, and r can't be 0. So what this does to a sequence or a series is that it has to be getting smaller and smaller and smaller. So for instance, if you got a sequence 8 plus 4 plus 2 plus 1, so the values are getting smaller and smaller and it's infinite, you can find the sum. R to the power of infinity will go to 0. On the other hand, if it's the opposite sequence starting at 1, so 1 plus 2 plus 4 plus 8 plus 16, that's an infinite series that has an infinite sum. There is no finite sum. There's no number there. So for our formula, as long as r is between, the absolute value of r is between 0 and 1, then we can just sub 0 in for Rn, and we get the formula a over 1 minus r, which is probably the easiest series formula that we have. So this is the formula for an infinite geometric series.